Pleasure to introduce Dr. Samuel Yen-Chi Chen. He received his PhD and BS in physics and an MD in medicine from the National Taiwan University in Taipei City. He's now a senior software engineer at Wells Fargo. Before that, he was a computational scientist at Brookhaven National Lab. His research interests are mainly building quantum machine learning algorithms and applying classical machine learning techniques to solve quantum computing problems. And he won the first prize in software competition from Xanadu Quantum Technologies in 2019. And today he's going to talk to us by a title called When Reinforcement Learning Meets Quantum Computing. The floor is yours, Sam.
Okay. Can you see my slides?
Yes.
Okay. So thanks for the introduction, and let's get started. Hello everyone. I'm Samuel from Wells Fargo. In this talk, I will introduce how the reinforcement learning algorithms can be combined with quantum computing, as well as some applications. This is the today's agenda. So the first section is to motivate the development of a series of research. And then I will introduce the very basic idea of what reinforcement learning is. And then based on this, I will introduce how reinforcement learning algorithms can be implemented on quantum computers. Here, I will solely focus on using the variational quantum circuits, or sometimes called the parameterized quantum circuits. And the next section is that I want to use the classical reinforcement to solve certain quantum computing challenges. And here I will focus on the quantum architecture search problem. And finally, I will give some conclusion and outlook. Okay. So since 2016, the AlphaGo drew a very significant attention of the development of AI and the machine learning techniques. And one of the critical part in the success of AlphaGo is the deep reinforcement learning. Concurrently, the development of quantum computing hardware is also very significant. Since also 2016, IBM provides cloud-based access to real quantum computers, the near-term intermediate quantum devices. And today, several big companies and also startups are working on delivering larger and larger scale quantum computers. So with these great achievements in the both fields, reinforcement learning and quantum computing hardware, so we may ask the question, can we merge these two fascinating technologies? For example, a RL algorithm running on a quantum computer, or using reinforcement techniques to further improve quantum computers or quantum algorithms. So the first part is the reinforcement itself. So machine learning has three paradigms: the supervised learning, unsupervised learning, and the reinforcement learning. The supervised learning, usually we use supervised learning to do classification tests, regression, or function approximation. The simplest example is that, you build a convolutional neural network or multi-layer perceptrons to classify photos from, say, cats versus dogs. So this is the very the simple one. And the unsupervised learning. So in the unsupervised learning, we don't have the label. We don't have the label for cats and dogs, but we have a lot of data, and these data have their own features. So we use unsupervised learning to clustering to put them in different groups. And the third one is today's topics, the reinforcement learning. The reinforcement learning is different from the supervised learning and unsupervised learning because it is a machine learning framework that try to train a computational agent in an interactive environment via trial and error. So in in each time step, the agent will execute an action to the environment, and the environment will evaluate how good or how bad the action is, and the environment will move on to another state, and then the environment will feedback a reward. So if the action is good, then probably there is a positive reward, and if the action is bad, then there's a negative reward. Also, the environment will feedback a state to the agent. So the state is the current observation of the environment, and probably the state includes all the information of the environment or only partial information of the environment. So as you can imagine, if the environment only presents a limited part of its actual state or the observation, then it's more challenging to learn how to make good decisions. The goal of a reinforcement agent is actually simple. It tries to maximize the total discounted return in an episode. So an episode is that, so from the start, say if you are playing a video game and you can make several decisions until the game ends. So this is a single episode. So you want to maximize the total reward that you got from the environment. So this is the idea. And there are a lot of different kinds of algorithms try to learn or train the agent so that it can maximize the total return. Okay, so let's move into the quantum reinforcement. So the quantum reinforcement is that we want to build a quantum agent so that the agent has some quantum components and it can interact with the environment. And then finally, we can tune the quantum parameters so that it can achieve a very high total return during the episode. But before we dive into the details of what is a quantum reinforcement agent, I need to clarify some terms in the quantum machine learning in general. So the quantum machine learning can usually be divided into 4 categories based on the algorithms and the data they process. The CC stands for the classical data and the classical algorithms. It is not a quantum machine learning actually, but we keep it here for completeness. The CQ stands for classical data and quantum algorithm. It is the very hot topics recently, since most of the big data we have are classical. And we hope that there are some quantum algorithms to help us dealing with the increasing complexity and volume of the data. The QC stands for the quantum data and the classical algorithms. Sometimes it refers to the subject of machine learning for quantum physics, which uses classical machine learning to study quantum phenomena. So if you use a classical convolutional neural network to study the quantum phase transition, then it's in this category. And the QQ stands for the quantum data and the quantum algorithms. So this is the most typical one since both parts are not yet fully understood. But a notable example is the quantum sensing applications. So if we have some quantum sensors and you use these quantum sensors to measure and you have some quantum state and you want to use a quantum machine learning or other quantum computing algorithms to process this state, for example, to reconstruct or do some other inference, then it is in this category. Today, we will focus on the CQ part. And for the second part of the talk is in the QC because we use the classical algorithm to study some quantum computing challenges. So for the CQ that we want to study today, we base this a series of studies on the hybrid quantum classical paradigm. So this is a particular paradigms that are suitable for currently available NISC devices. The idea is that certain part of the calculation are performed on the quantum computer, while the optimization procedures, such as the gradient calculation, is carried out on the classical computer. So with this framework, we can easily apply the optimization method developed in the classical machine learning community for very complex architectures as the ones that I will describe later. Instead of training on real quantum devices, which is not that easy to access today, we can also train on the model using quantum simulation software with some high-performance computing backend. Because these variational circuits may need a lot of circuit evaluation, and it's a little bit difficult to allocate these quantum computing times at the moment. Okay, so in this hybrid quantum classical framework, the basic building block is the variational quantum circuit or the parameterized quantum circuit. So this is a particular kind of quantum circuit with tunable parameters, and these parameters are subject to iterative optimization procedures. These procedures may be gradient-based, for example, a lot of gradient descent method, or other search method or heuristic methods, such as the evolutionary or genetic algorithms. And the generic idea of a variational quantum circuit is that it includes three basic components. The first is the encoding circuit, the U of X here. Since we are dealing with the classical data, so we need a particular way to transform these classical data into the quantum state. And usually, this encoding circuit is not trainable, and we need to define how we want to encode the data into the quantum state. And this is a very important step because this usually will have a lot of influence on the quantum advantage that you may have. And then the variational circuit is the part that with tunable or trainable parameters. So this is so you can see this the analog of the classical neural network weight. And then finally we do the measurement. So we need to retrieve the information from the quantum circuit. So the quantum encoding problem is that, so we have an NQB system. And so we all know that the NQB quantum state can be represented as the superposition of all the basis state, the C complex number amplitudes. And what we want to do is to find or define a particular circuit that can transform a classical vectors into these complex amplitudes. And there are several kinds of encoding or state preparation method, and different encodings have their strengths and weakness. Two mainstream methods are the amplitude encoding and the variational encoding. So in the amplitude encoding, the idea is pretty straightforward. So you have an n-dimensional vector, and you just want to transform it into the log to n qubit system, because it will have the exact number of amplitude. And another way is called the variational encoding. So you use the input number x1 to xn as the quantum rotation angle to rotate the initial quantum state. And this is easier than the amplitude encoding because it only requires some, say, single qubit rotation. But as you can see now, this method cannot give you a lot of advantage regarding the number of qubits. But this is a very common way because you see quantum computers are pretty noisy, and it's difficult to build a very deep circuit simply for amplitude encoding the state. And also in the hybrid quantum classical framework, we can combine multiple components from quantum and classical world in a way such that a directed acyclic graph, DAG, is formed. And different classical neural networks and quantum circuits can be connected into a complex model. In principle, the whole model can be trained in an end-to-end manner. As we will see later, the classical paths can be some quantum-inspired algorithms such as tensor network or just a neural network. The output from either the quantum or classical node can be further processed with a loss function. For example, if you want to do the classification task, then you will use the cross entropy loss. And if you want to do the function approximation task, then you will use the mean square error, for example. And also, we can use other gradient-free methods such as the evolutionary optimization. The next question is that how to calculate the gradient of a quantum node. So let's have the very simple example here, the variational quantum circuit with the encoding circuit, U of 0 and some single qubit rotation gate, and then finally we do the measurements. So this is a step-by-step illustration of how a variational quantum circuit works. So you put in the input vector x, and you encode into a state, and you will pass through some variational or rotational gates, and then you measure the qubits, you get the expectation value. Usually we get say the poly Z expectations. So the measurement or the expectation or the observable is the so-called quantum function. So the quantum function, the output of a quantum function is some classical values, because only classical values that we can use it to calculate the loss and update the values of these quantum parameters. So we have this f quantum function, and we want to calculate the gradient of this quantum function with respect to its quantum parameters. And based on a seminal work by the Mitarani et al. From the Osaka University, they show that the analytic gradient of quantum function can be calculated as follows. So the idea is that you need to run two circuits with parameters shifted by pi over 2. And this will give you the analytic gradient of the quantum function. And do not confuse with the finite difference method, because we don't need the infinitesimal here. So this is more numerically stable. But as you can see, there are some challenges here. So if you want to optimize the model with a lot of parameters or a lot of data points, then you need to run a lot of circuits on the quantum computers. So sometimes it is a bit challenging to do this now, because the quantum resources are a bit limited. Okay, so with these tools in mind, then we can think about how to build a quantum reinforcement agent. So so this is a slightly modified version of what a reinforcement is. So in the reinforcement, we have the agent. Now it's a quantum circuit, and we have quantum circuit parameters here. And this quantum computer or a quantum simulation software will interact with the environment. So the environment will be a navigation problem, a channel selection problem, or a control problem, or a video game. But we are considering the hybrid quantum classical method, and we have something need to be done on the classical computer. So we add another part here, the classical optimization part. So these are a lot of different ways to optimize the quantum circuit parameters. So the gradient descent is the one that we want to use. You can also consider other methods, for example, the finite difference or other modified version of the gradient descent, or some other non-gradient methods such as the evolutionary algorithm. So the first try in the quantum reinforcement is the quantum deep Q-learning. And the deep Q-learning is the work released by DeepMind in 2015. And it's a milestone in how neural networks can be trained to learn reinforcement for sequential decision tasks. So we want to extend this idea in the quantum regime. So we propose the quantum deep Q-learning, and we try to use the quantum circuit to do what can be done in the classical world. So we keep the original idea of the target circuit to make the numerical training more stable, and also the replay memory. So for example, the agent can interact with the environment, and in each time step, it will have the state, the action, and the reward it gets, and the next observation. So this is the transition pairs, and we store the transition pair in the replay memory, and we use this replay memory to optimize our quantum circuit parameters. And we test on a very, very simple example. So at the time when I designed this kind of algorithms, we don't even know it will work or not. So I tried a very simple one to have an idea. And the environment that I chose is called Frozen Lake. So this is the standard environment in the OpenAIG, which is the standard benchmark environment. So in this environment, there are 16 discrete states labeled from 0 to 15, and there are only 4 actions. So the agent is expected to navigate from the starting point, A, labeled as S, to the goal labeled as G. And if the agent steps into the hole, labeled as H, then it will get a negative reward, and the episode will terminate. And also, I want to train an agent using fewer steps as possible. So I also designed the environment to give the agent a small negative reward at each step. So the first challenge is how can we design the encoding circuit. So at that time, not many qubits are available, even for the simulation. And in this particular environment, there are only 16 states. So we can use 4 qubits to represent the binary string from 0 to 50. So we can use the variational encoding to do this task. So this is sometimes called the computational basis encoding, but I believe it is just a specialized variational encoding. And we try with different environments, for example, this one, and we found that after 200 episodes, the agent will converge to the perfect scores. And we also try with different environments, and because we don't want to have the algorithm which can only succeed in a particular environment. So we try the different ones, and they all show a very promising result. The next step is we want to use in a more real world use case. So this is a software-defined network application called cognitive radio. So the agent is expected to find or have to choose the radio channel when it doesn't have the knowledge of what the primary user will choose. So in the left-hand side, I show some different kinds of patterns that the primary user will choose, but the quantum RL agent doesn't have this information. So it requires to learn the fact via trial and error, and we test on different environment. For example, this pattern or other more strange patterns, and we found that the quantum RL, especially the quantum deep Q-learning, can capture this knowledge pretty fast, and we can compare with classical method. For example, the Q-learning, the tabular Q-learning, use an array to store all the values, or the classical neural network based deep Q-learning or the quantum deep Q-learning, and we can see that at least within this particular experiment setting, the quantum deep Q-learning can achieve the comparable result with a small model size. But now we have the quantum deep Q-learning, but the environment in the real world is much more complex and probably not fully observable. But if we consider the partially observable environment, in partially observable environment, which is the case in many scenarios that we want to solve, the information that an AI agent can get is not enough to decide the next move. So under these scenarios, the agent may need to have the capability to memorize previous steps so that you will have enough information to carry out decision making. And among several different models, the quantum neural networks is one of the VQC-based model to have the capability to memorize sequential events. And so it is a good candidate to investigate whether QRNN can be used as an RL agent, because the quantum recurrent neural network has been shown that it can learn time series, but no one knows whether it can be used to learn partially observable environments. So we extend the quantum deep Q-learning into the recurrent setting. The major difference is that when we sample the batch from the replay memory, we sample batch of trajectories instead of the individual transition pairs. And we also consider the classical benchmarks using the classical LSTM with similar model size. So we show that under these conditions, the quantum model can perform better than the classical model. So what is the perform better means here is the higher score or more stable score. So if you see the right-hand side, the quantum recurrent RL agent can reach pretty good scores. And you see that sometimes the classical model can also reach that high score, but it quickly collapsed into zero, so that the training is not stable, and it's not something usable here. But one of the challenges that we face during the training of these quantum RL agents, for example, the quantum DQN and the recurrent quantum reinforcement, is that the requirement of computational resources is pretty high, especially if you are using the simulation software. And most of the time, the multi-core CPU resources is not fully utilized. So if we want to explore more realistic use cases or more complex testing environments, we may need to speed up the training. And one of the intuitive idea is to do the parallel or distributed training. So here, we consider the asynchronous update of the quantum RL agents. So the idea is that there is a shared global memory to keep the model parameters. And there are some parallel instances, and each instance will have its local circuit parameters and its own instance of the environment. So the agent will play with the environment individually, and then update its parameter, and then submit the gradients to the global memory, and use this parameter to update the global parameter, and then get the updated version of the parameter. The asynchronous training means that we don't need to wait for all the agents to complete its own episode. So when a particular agent finish its episode, then you will do the gradient calculation and upload to the shared memory, and then get the result. And this will increase the sampling efficiency, because in a given time step, there are several agents running in parallel, and they may encounter different states. So it will diversify the state or the observation that the agent can get, and it will make the training stable, and we can use multi-core CPU, so it's also much more faster than the original single-threaded training such as the QN. So we consider different kinds of the environment. These are all the standard benchmark in the Gene OpenAI Gene. For example, the Aquabot, the Carpal, and then another is the grid navigation task. And we can show that in all of these environments, these asynchronous training can beat the classical model when the number of parameters of classical and quantum models are similar. But gradient-based methods, they have some challenges, and they may suffer from some local optimal, which is a well-known issue in the classical reinforcement community. Also, certain QRL models are very difficult to train using the gradient-based method. So in classical evolution optimization, sometimes can beat gradient-based methods. So we want to ask whether it is the idea in the quantum RL. The evolutionary optimization idea used in this work are pretty simple. So we initialize a population of agents, and these randomly initialized parameters are just sample from the Gaussian, and we can evaluate the agents, and then we run several times to get their average, so that the model is more stable, and use this average score as the fitness of the model, and we use the top T agents to generate the next generation. And how can we generate the next generation? We just add some random noise, a small random noise of these best performing agents, and then we can have the next generation. And also, we try again on the carpal task, and we show that, okay, so after 1,000 of generations, it can reach a pretty good result. But I want to emphasize that here, the quantum agent is only a 2-qubit system, and using the amplitude encoding. So in the carpal environment, there are four values for the observation, and if I use the amplitude encoding, I only need 2 qubits. And we can also use this method to study these navigation tasks. But this particular task has 147 dimensional vector. But at that time, we don't have a 147 qubit quantum simulation, so we need some particular architecture to reduce the dimension of the input to a latent vector so that the quantum agent can process. And we choose the tensor network, particularly the matrix product state, to do this task. And we show that such tensor network VQC hybrid model can perform very well. And if we compare with the similar size, the neural network and the VQC model, we see that in all three cases, the tensor network enhanced model can beat the classical neural network model. So it opens another way to study the hybrid model, because the tensor network is a quantum-inspired architecture, and in general, you can transform a matrix product state into a quantum circuit. So if you have a much larger quantum computer in the future, then you can use this to replace the matrix product state. So the next part of my talk is to use the reinforced learning for the quantum architecture search. So the task is this. So we have a quantum computer and unknown noise pattern, and I want to have a quantum state, but I don't know how to put the gates on the quantum computer so that I can get that state. So I want to train a classical reinforcement agent that it will put a particular quantum gate to the circuit, and then the quantum computer will evaluate. So I know what the quantum state I want, so I can calculate the fidelity of the state and the state that the RL choose, and then feedback to the RL agent. So if it is say 0.99 fidelity, then it will give the RL agent a positive reward. And the observation that the RL agent can get from the quantum computers are just probably XYZ expectation value of each qubits. And we also want that the agent to use few gates as possible, because in the NISQ area, the deep circuits very difficult to run, and the fidelity is usually low. So we consider the deep Q learning, the original deep Q learning, and the policy gradient method. So the policy gradient is that, okay, so we have the classical neural network, and the neural network can generate a particular action. The neural network output is the probability distribution of the actions. And we calculate the gradients directly of these policies with respect to these neural network weights. And I'm not going to explain the details of policy gradient algorithms here, but the fundamental is that the reinforced algorithm. So the parameter theta are updated along this particular direction. But usually these reinforced algorithms is a bit unstable. So to reduce the variance, more modified form is called the using the baseline. For example, you use the baseline, so your a reward will subtract the baseline, and this is this will make the training more stable. And a particular choice for the baseline is the value function. So the idea is that, okay, so given a state and there is a value function, and your Q function can subtract that value function to compare or to have an idea how good or how bad the action compared to the average value. So this is a more efficient policy gradient method. A further improved form is called the proximal policy optimization, because if the update of the policy is too large, then the learning will also be unstable. So the idea in the PPO is that we limit the update the scale of the update for the policy. And we compare these two classical RL algorithms on our quantum architecture search challenge. The first is the really simple 2QB Bell state. I believe all of you know this circuit and this state, but here I want to train an agent to find out this architecture, the Hadamard gate and then the CNAR gate, without any prior encoded physics knowledge. And we compare the advantage actor critic policy gradient and the PPO for this challenge, and we found that the RL agent can find this textbook answer pretty easily. So the next is to test it on a more challenge task, the CQB system, and we found some difference here. So the PPO can reach the optimal solution much faster than the original advantage actor critic one, and this is within the expectation because the PPO usually have a more stable policy update. But in a more realistic situation, we have some devices which are noisy, and the noise pattern usually drifts with time. And if we want to do calibration or train a new reinforcement agent against this particular new environment, then it is very expensive in general. So we want to study the lifelong or continual reinforcement for this quantum architecture search challenge. The method that we choose is called the probabilistic policy reuse. So our RL agent can sample from some previously trained policies and use these policies to guide the training of the new policy when the agent encounters a new environment. So the idea is that, so initially we have, we need to train the agent from scratch, and then we say the model of that particular environment. When the agent encounters another environment, it will sample from these old policy libraries and then use this policy library to sample some good transition pairs, and these transition pairs will be put in the replay memory. And since we have the assumption that the environment, although they are different, but they are they share a lot of similarities, so they are not completely different. So old models may be better than a randomly initialized agent. So we use these previously trained agent to guide the training of the new policy network. And you can also see that we use this particular method to distill the knowledge or the information from the older policies. So the algorithm is that, so we have a task and we have a policy library, a lot of library trained on the previous environments. And then we probabilistically using the new policy or the old policies. And the core of this algorithm is that we have a temperature softmax to function to sample from the policy library. So if a policy is good, then the W value will be higher, and it will have a higher probability to be sampled, and these old policies will be used to help the training of the new policies. Okay, so the probabilistic policy reuse is not that new, but in this work, we combine it using the deep Q-learning, including the experience replay and the target networks, so that these old ideas can be used with the modern neural network-based reinforcement learning, and we tried it on some noisy circuits implemented using the Q-skin simulation software. So this is the first example. This is a noisy-free training from scratch case, and if we add some noise to the X gate, say 0.05, then you can see that if I can base on some say noise-free policies, then the agent will quickly learn how to synthesize the quantum state. And we can also add more noise on different gates. And we show that, okay, if the agent can sample from previous policies, then the learning is much more faster than the training from scratch one. And also for even if we add more noise on the 2-qubit gate, then the results are still similar. So here's our conclusion. So the encoding and embedding methods are pretty critical, and we can use both gradient-based methods such as Iris-Borg Adam or the evolutionary algorithm to optimize the quantum agents. And we can use the quantum recurrent neural network to enhance the quantum RL with memory of the past events, and asynchronous training can be used to reduce the training time of the QRL in some more challenging tasks. And we can use classical reinforcement algorithm to find the quantum circuit architectures under various noise patterns. And we can also use the previous learned policies to help the training or guide the training of the new policies for unseen environments, for example, the changing noise environment. And there are a lot of applications of this RL-based method, for example, quantum architecture search, quantum compiler, and quantum error correction. So that's the end of my talk. Thank you.
Okay, let's thank Sam. And are there any questions or comments? Okay, it looks like there's not questions or comments anyway. Thank you again, Sam.